Another previous year question. Test convergence of the infinite series 2 by root 1 plus x square by 3 root 2 plus x raised to 4 by 4 root 3 plus x raised to 6 by 5 root 4 plus etc. Here we wish to write down the general expression of general term un. You can notice that if you select the number appearing inside the root as n, then the number appearing outside the root can be expressed as n plus 1, because everywhere in each term you can see that inside the root number, when incremented by 1, you obtain the number outside the root in every denominator. 1 plus 1, 2 is appearing outside the root. If you consider 3 as n, then the number outside the root in the denominator can be obtained by evaluating n plus 1 or 3 plus 1. So in general we have denominator of the format n plus 1 into root n. But how will we generalize the power of x in the numerator? You cannot write n as the power in the numerator, because you can see that all the powers are even. So n must be, or the power of x must be an even quantity, and you cannot write 2n also, because there is a relationship between the number that appears inside the root in the denominator and the power written here. The relation is clear by looking at examples. 2 into 2 minus 2 gives the power of x here. 3 into 2, 6. 6 minus 2, 4 is the power of the x here. 4 into 2, 8. 8 minus 2, 6 is the power of x here. Similarly, 1 into 2, 2. 2 minus 2, 0 is the power of x here. So the general power that can be given for x is obtained as the power is 2n minus 2, where n is the number appearing inside the square root. So in general we have un equals x raised to 2n minus 2 divided by n plus 1 into root n. Looking at this expression, we can write un plus 1 by just replacing every n in this expression by n plus 1. So when you replace n by n plus 1 here, you have x raised to 2n plus 2 minus 2. 2 and 2 get cancelled. Therefore, un plus 1 has numerator x raised to 2n. Similarly, you have to replace every n by n plus 1 to obtain un plus 1. So this is the expression of un plus 1. We'll be making use of D'Alembert's ratio test to solve this problem. Ratio test says that if we have a positive term series summation un, then limit n tends to infinity un by un plus 1 happens to be a quantity k, and if k is greater than 1, then the given series will converge. If k is less than 1, then the given series will diverge, and if k equals 1, the test cannot give us any conclusion, so we have to take up other methods. When we apply the limit to un by un plus 1, if we obtain a value greater than 1, we will conclude that the given series is convergent. If we obtain a value less than 1, then we will conclude that the given series is divergent. So as to apply ratio test, we evaluate limit n tends to infinity un by un plus 1. We write the expressions of un and un plus 1. We can group terms containing x. So we have x raised to 2n minus 2 into x raised to 2n. This quantity, when taken to the numerator, it becomes is equivalent to multiplying the reciprocal of this denominator to the numerator. When x raised to 2n becomes the denominator when taken to the numerator, when we multiply the reciprocal of this quantity to the numerator, we have x raised to 2n minus 2 is multiplied by x raised to negative 2n. Instead of writing x raised to 2n minus 2 divided by x raised to 2n, we can write it as x raised to 2n minus 2 into x raised to minus 2n, because 1 by x raised to 2n equals x raised to negative 2n. Similarly, we group the terms n plus 2 divided by n plus 1. This n plus 2 when taken to the numerator becomes the numerator of the expression. Therefore, we have n plus 1 in the denominator. This n plus 2 becomes the numerator. So, we grouped terms. Similarly, when we group the terms with square root, we have n plus 1 becomes the numerator and n becomes the denominator with the power 1 by 2 instead of writing square root. Now, when we compare these two terms, we have x raised to m into x raised to n equals x raised to n plus n. Therefore, 2n minus 2 plus 2n will occur in the power for x. So, after cancelling 2n and minus 2n, we are left out with only minus 2 in the power for x. Therefore, after cancellation, we have x raised to minus 2 as the expression when we evaluate multiplication here for exponents, applying the exponential law. Now, we may divide the numerator and denominator of these both expressions by n, so that we have, when we divide this expression on numerator and denominator by n, we obtain 1 by 2 by n, 1 plus 2 by n divided by 1 plus 1 by n. Similarly, when we divide this expression by n for both numerator and denominator, we obtain 1 plus 1 by n divided by 1. We are always dividing by n in the numerator and denominator part because we know that limit n tends to infinity, 1 by n can be written as 0. So, here 1 by n, 1 by n, 1 by n after application of limit n tends to infinity will become 0. So, we are left out with 1 plus 0, 1 plus 0 which is 1 itself. Here also we have 1 plus 0 by 1 which is 1, the whole raised to 1 by 2 which is again 1. So, after application of limit, we are left out with only the quantity x raised to minus 2. We have to apply limit only to expressions which have n. X raised to minus 2 is independent of n. So, even after application of limit, it comes out without any change because it does not involve any term of n. By ratios test, we have whichever answer we obtained after evaluating limit n tends to infinity un by un plus 1. This particular series will converge if the limiting value is greater than 1. So, we have obtained x raised to minus 2 as the limit. So, we are expecting the given series will converge only if x raised to minus 2 is greater than 1 by following the ratio test. Instead of writing x raised to minus 2 is greater than 1, we can also write x raised to 2 is less than 1 because x raised to minus 2 can be written as 1 by x square, and if we take x square to the other side, in this side we are left out with 1. Therefore, it becomes x square less than 1 for the given series to be convergent. We have x raised to minus 2 greater than 1 rewritten as 1 by x square greater than 1. We can cross multiply x square to the RHS, then we get the inequality 1 greater than x square, that is summation un converge if and only if x square less than 1. And in x square greater than 1, we will have summation un will diverge. This is written looking at the conclusion we have observed in the ratio test. If this limit is greater than 1, un will converge. If this limit is less than 1, the given series summation un will diverge. So, if x raised to minus 2 is greater than 1, un converge. That is, we obtain x square less than 1 is the position where summation un will converge. So, the opposite of this inequality will be the position where summation un will diverge. That is, x square greater than 1 will be set of values of x where the given series will diverge. But we don't know about the situation of given series at x square equals 1. Because here by test we have at the limiting value equal to 1, test fails. So we have to look up for some other methods to check the behavior of the given infinite series at x square equals 1. We must have written x raised to minus 2 equals 1, but it is equivalent to writing x square equals 1, because x raised to minus 2 is equal to 1 by x square. Therefore, x square equals 1 and 1 by x square equals 1 are equivalent expressions. Now, since we have un equals 1 by n plus 1 into root 2, since we substituted x square equals 1 in the original expression of un, that's why we obtained un equals 1 by n plus 1 into root 2. We may rewrite this as n raised to 3 by 2 plus root 2 when we multiply root n to inside the parenthesis. If we take outside n raised to 3 by 2 common outside, we are taking n raised to 3 by 2 common outside because we are familiar with the series summation 1 by n raised to 3 by 2. Summation 1 by n raised to 3 by 2 is of the format summation 1 by n raised to p with p greater than 1. So this series will surely be convergent as per the p test. So we are looking for a familiar series which is summation 1 by n raised to 3 by 2. In order to take outside n raised to 3 by 2, we will take n raised to 3 by 2 common outside root n, then it becomes 1 by n, because 1 by n into n raised to 3 by 2 will give you back root n. So after taking n raised to 3 by 2 outside from the denominator, this is our final expression of un. Now we evaluate limit n tends to infinity un divided by vn, where vn is the familiar series with the general term vn equals 1 by n raised to 3 by 2. So you can see that n raised to 3 by 2 get cancelled because it is common in the denominator part for both un and vn. So we are left out with 1 by 1 plus 1 by n. Limit n tends to infinity 1 by n is 0. Therefore, the final answer for this limit will be 1. Since we have obtained a finite quantity, we have by limit test summation un and vn behave similarly. That is, if the familiar series is convergent, then the given series will also be convergent. Since the familiar series we have selected is summation 1 by n raised to 3 by 2, which is convergent as per p test, the given series will also be convergent at the point x square equals 1. So in general, we have whenever x square is less than or equal to 1, the given series is convergent.